Chapter 10, Part 1, Introduction to Radical Chemistry. So far, in all of the reactions that we've learned and the mechanisms that we've learned, the general rule has been minus likes plus, or opposites attract. Reactions that have occurred so far occurred because of a Lewis acid or base interaction. Think of nucleophiles attacking electrophiles, or alkenes reaching out to attack something electrophilic. Electrons in these mechanisms move in pairs in order to make or break bonds or to show resonance. And the mechanisms are drawn with double barbed arrows. So for example, in the SN2 reaction of hydroxide with iodoethane, we see a lone pair from any one of these lone pairs on oxygen attacking the carbon that's attached to the iodine. Iodine has lone pairs of electrons, and iodine leaves with the electron pair in the covalent bond, giving us a molecule of ethanol plus iodide anion. This type of bond breakage is called heterolysis. Also, I want to point out again that the mechanisms are drawn with double barbed arrows. When we say barb, we mean the end of the arrow. A single barbed arrow, which we're about to learn about, looks like this. In radical reactions, something totally different happens. We have a process that's called homolysis or homolysis, where the electrons in the covalent bond each go their own way, and they leave with one of the atoms. This gives us a radical for each atom. So a radical is a single electron on its own. In radical reactions, the electrons move individually, and they are represented by single barbed arrows. Each atom takes half of the covalent bonds that had previously held them together. Radicals, also sometimes called free radicals, possess an unpaired electron. Radicals are reactive intermediates. They are not a final product. So even though this is drawn like a reaction, this would actually be just a step in a larger reaction. There are 3 steps in any radical reaction. There's the initiation, the propagation, and termination step. So let's talk about how radicals are produced. The production of radicals requires energy in the form of heat or light. So for example, dialkyl peroxides. You've seen ROOR used pretty frequently so far in our anti-Markovnikov additions. When these are exposed to heat or light, each oxygen takes an electron with it, and you end up with 2 equivalents of an alkoxyl radical. You can also see this with halogens. When a halogen molecule breaks apart to initiate a radical reaction, each atom takes one of the electrons from the bond with it, and you end up with 2 equivalents of halogen radical. Notice that the radicals do not have charges on them. They are not charged, they just have an unpaired electron. And the reason this works is that oxygen-oxygen and halogen-halogen bonds are weak, and so homolysis occurs readily. So let's talk about homolysis and bond dissociation energy. A covalent bond is cleaved and 2 electrons are divided equally amongst the products in homolysis. So again, showing you that mechanism, Each one of these atoms takes one of these electrons with it, breaking it up into two radicals. The bond dissociation energy correlates bond strength and radical stability and can be used to calculate enthalpy change. If the enthalpy change is positive, enthalpy change is positive for bond forming or formation and negative for bond breaking. So the bond dissociation energy for a hydrogen-hydrogen bond is 436 kilojoule per mole, whereas the bond dissociation energy for a chlorine-chlorine bond is 243 kilojoules per mole. So you can see the hydrogen-hydrogen bond is more stable. It requires more energy to break the bond. Let's talk about the structure of the radicals. So we're now familiar with some kind of bizarre forms of carbon. We've seen the carbocation, which is sp2 hybridized and trigonal planar. We've also seen the carbanion, which is technically sp2 hybridized, but comes across as pyramidal because of the lone pair taking up space. The radical kind of fits somewhere in between because it has a single electron taking up space, so it's not perfectly sp2 hybridized or trigonal planar. It's also not going to be pyramidal. The unpaired electron is still going to sit in an unoccupied p orbital. And it's the presence of that unoccupied p orbital. Sorry, I think that I meant to write unhybridized. And it's also unoccupied at the time. Unhybridized p orbital is what makes all of these sp2 hybridized, even though the carbanion doesn't look quite like it. So let's talk about the reactions of radicals. We're just going to touch on this briefly, and then the next video will actually talk about specific reactions. So most small radicals are highly reactive. They react in order to pair their unpaired electron. If a radical is reacting with a non-radical, a new radical will be formed. This step is called propagation. If a radical is reacted with another radical, a covalent bond is formed and the radical is killed. This step is called termination. So before we move on to the reactions of radicals, let's talk about the relative stability of radicals. Fortunately, it follows the same rule as carbocations. The more substituted a radical is, the more stable it is. So tertiary radicals will be preferential over secondary, which is better than primary, which is better than methyl. And this has to do with the bond dissociation energies. There's more energy required to break the carbon-hydrogen bond on a methyl than on a tertiary carbon atom.